Okay, I believe this is the slide we're on. As soon as we get, let me, okay, first I have a question. Did all of y'all get the word in time, or did any of you show up Monday? You did show up? Sorry. We didn't get it until Thursday afternoon. I mean, it was a surprise to me. And did they send it to the students? The announcement? What's that?
I just looked on the website.
And did you?
There was a little message that said it was closed yesterday.
That what?
There was a message that said it was closed
Monday.
yesterday.
Okay. So that was after you got here?
Yeah.
Sorry. Was the building all locked up, or was it open? Huh? The gates were closed. Sorry. Yeah, Monday. Yeah. So it came as a really surprise. I was planning to be here. In fact, we had arranged our holiday weekend, so I would be driving back Sunday and loved everything, and then came up Thursday afternoon with, what? Okay. So I didn't drive back Sunday. But sorry y'all didn't get the word. If I had put it on Blackboard, would you have seen that?
Probably, but they tell us, hey, check your email if the school's going to be closed. Instead of on the email, they put it on the front page.
Oh, so they didn't put it on email.
No, at all.
Yuck! What I saw was only sent to faculty. I thought, well, they must have sent something else to students. That is so bad. I apologize for the school. That was poor. I'm glad you told me that. I'll bring that up next time they say, and students should check their email. I say, well, if you're going to put something like school closing, you should put it out there. But students begin to think you're not going to put it there. So gave me a little ammunition for one of my favorite. Never mind. Okay. Well, one decided to make it today. Okay. And Cinco de July, huh? Okay. Okay. All right. Here's what I was going to say. I think I announced this last time we met a week ago, Wednesday, that I had been put on a biology search committee, screening committee, or whatever you call it, and that ate up most of my week last week. Any office hours I had and stuff at home. I was at home and on the road and everywhere working on that over the weekend. But I did get everything that's been turned in graded. What I didn't get was it put on Blackboard. I got that close, but then things came up and I just couldn't get it done. So I won't be able, I have no time today to put things on Blackboard, but beginning tomorrow, hopefully I will. But that biology search or screening committee has some other really bad implications. They can call for interviews any day. And I've said it over and over and over. Please don't do Monday or Wednesday because I've got classes 8 to 9. So Tuesday, Thursday would be better. That means they'll probably put it Monday or Wednesday. And again, they'll probably give me that much notice. So if I hear that I'm going to have to do interviews on Wednesday or Monday or Wednesday, and they don't give me a lot of time, like the previous class, to know that, then it is going to be pretty bad. I'll put something on Blackboard and they'll send an email and all that kind of stuff. But I do not know now. So okay. I think that's all I need to say. I've probably said too much. Okay, any questions on anything we've done up till now? Like I said, I'll try tomorrow to get everything on Blackboard and attendance and that kind of stuff caught up. It's just been crazy. Okay, now I can't remember if we did this slide or not. Do y'all remember? It seems like we did. This was, yeah, this was, no, I think we did that slide. Okay. think this is the one we need that we start with today. Sorry. Okay. My mark in my book has us on page 153, chapter 3, differentiation, section 3.5, higher derivatives and graphical insight at the top of page, or near the top of page 153. And the question is, can we visualize the rate represented by f double prime, second derivative of f with respect to x? Let's say that this is our function, okay? They have one of these colored wrong, and I don't know why. This straight line should be pink, not blue. This is the function. The blue parabola here is the function, okay? Now, that's your the function. Your first derivative is the rate of change, rate at which this function is changing. And up here, the slope is very negative, but not changing by much, right? The tangent lines up here are not changing by much. But then you get closer to where the bend is, and the tangent lines are changing big time. What that means for you is the first derivative starts off negative, okay, and then goes to 0 rather quickly down here, and then increases and is positive from then on. Well, the first derivative is not changing much at all here. It's changing very rapidly here, and then it's changing slowly again out here. So that means the second derivative is fairly large here, okay? Now, which direction? Well, the slopes starting off very negative. I don't mean to say very negative when Davis walks in, but I think I just marked Ting and Davis's spot, and now I'll mark Davis. Okay, you're both here. Got it. Okay. The first derivatives are very negative, getting less negative all the time, meaning the second derivative is slightly positive here. Very positive here because it goes from fairly negative to not so negative to 0 to positive very quickly here. So that means the rate at which the first derivative is changing is large, and it's large positive. So that's why they say the large second derivative here. The tangent lines are turning rapidly. Okay? Now, what they're not saying is if you had a parabola going like this, then the first derivative would be positive, but getting less positive, so then it would be a very large negative second derivative. We'll get to that later. On this curve, however, the second blue curve, and this is, find you, Lauren. Have to go all the way across the page. Okay. Yeah. Good deal. The first derivative starts off negative, but not so negative, but then gets slightly less negative, so the second derivative will be very small positive number, and they're still changing very slowly here, so the second derivative is again positive, but a very small positive number. A little more positive here than it was up here or here, but still positive. Tangent lines are changing direction very slowly. What about that one? Now that to me should be a blue one. This is a straight line. What's the first derivative? There's a couple of answers you can give me. Give me one. What's the first derivative of a linear function? Say that.
Would it be the Y-SO formula or no?
Okay, that would give you the tangent line for it, and the tangent line is the function, So basically, the first derivative is the slope of the line, right? Because first derivative is slope of the tangent line. The tangent line is the line, so therefore the slope of that line is the first derivative. Now, how is that changing? How's the slope of that line changing? Tangent line at any point here. Let me ask it this way. Is it changing? No. So therefore, what's the rate of change of the first derivative? Zero. Very good. Okay. The second derivative is zero. The tangent line does not change because the tangent line is the line itself, because it's a linear function. Okay. I think we're ready for example 6. I believe they do too much for us here, but we'll take a look anyway and see. Okay. Identify curves 1, over there, 1 and 2, okay? In figure 4b, the second one there, as the graphs of either f prime or f double prime for the function f. The blue is the function f. Smiley face there. Okay? Now you identify for me what the graph of the first derivative is. Is it Roman numeral 1 or Roman numeral 2? Why do you say that? What comes first? No, that wouldn't be it. Okay. And here's Shakina. All right, good deal. It may be right. I'm just asking why you chose one. Looking for the first derivative of this blue curve here. Okay, we're choosing either Roman numeral 1 or Roman numeral 2 curve there.
Okay, so this over here is negative. That's the first derivative.
The first derivative is negative here.
And that's the second derivative. So it changes signs and then positive. So
Okay.
at 1, from A to B goes from positive to negative. And graph A goes from negative to positive.
Okay. So you're still sticking with 1.
Yes.
Okay. Now you just told me the first derivative is negative here. So we're saying at A, the first derivative is negative. Am I understanding correctly? At A, the value here is positive. So it can't be that one because you just said the first derivative was negative here. So it looks like it's that. Okay? And let's see if that continues. What's the first derivative down here at this midpoint? 0. And what's this one's certainly not 0 there. This one is 0. And then after that, the first derivative is positive. So 2 is the graph of the first derivative. Okay? How about the second derivative? Would that be 1? Well, let's see. It may or may not be. How is this changing here? Now, I do not quite agree with this, but see, it looks like to me that slope of this is almost 0. That's not nearly 0, or it doesn't look like it. This has a positive slope here, and this is positive. Positive slope, positive slope, positive slope, positive slope. Yeah, the slope is always positive. That looks good. But the slope is increasing quickly here not increasing at all because that's almost a straight line there. And when the slope of a straight line is not changing. So there, this, and then it goes, that it's increasing less positively, but still positively. So therefore, this is less positive than here, but still positive. So that will be the slope of the second derivative. The only part I don't like about this looks like this is far closer to 0 than this is. But they don't give us the scale, so that it's probably okay. And again, this is getting close to 0, and that doesn't look like it. It seems like to me that should be lowered a little bit. But that's just me. Okay. You agree? Any questions on that? Okay. So the first derivative is 2, Roman numeral 2. Second derivative is, the graph is Roman numeral 1. That is the last example in section 3.5. There is a summary here, and I think you should know that, but if you use it as a review, do you want to do preliminary questions or not? Yay or nay? Would they be helpful or not? Preliminary questions. Let me know. Did I hear a no? I thought I heard something rattle. Okay, no. Okay, all right. Then the homework exercises are any of the odds 1 through 15, any of the odds 17 through 25, then either 27 or 29 or both, any of the odds 31 to 35, and then you got a whole bunch, any of the odds 37 to 51. Now, some of those toward the end, like 51, says you need computer algebra system. You may or may not. You can play with it if you like. If you get too bogged down with it, just don't do it. But that would be, I would do more than just one of those. I would do several of each type, a few of each type, just to make sure I understood what was going on. And by the way, I hope you've noticed that the homework questions are very similar to the test questions, so you can make your test go by much easier if you work with more of the homework exercises. Then you'll be familiar with them, and the test will not be quite so daunting, maybe. All right, further insights and challenges. I'll let you decide whether you want to do any of those. There's only a couple, 53 and 55, but you don't have to do those unless you want to. So, that is the last slide. So let's leave that and go to 3.6. If I can get it to open. It doesn't say, there it goes. Very slow. It took forever for PowerPoint to open first thing this morning. I was in here several minutes ahead, and well, that didn't take so long this time. So let's do the slideshow from the current slide, and we will start here. Okay. This book sure isn't like my professor for Calculus 1 was. He did not give us the theorem before we proved it. We had to prove it, and then he said, now this is the theorem. One thing to note before we do anything else. In calculus, always assume your trig functions are measured or evaluated in what mode? Radian mode. Do not try to do them. They do not hold in degree mode. They do hold in radian mode. Okay? Unless you see them specified, otherwise assume they're always in radians. Okay? there is a little blurb in your margin, left margin, right at the beginning of 3.6. In Theorem 1, we are differentiating with respect to x measured in radians. Derivatives of sine and cosine with respect to degrees involve an extra unwieldy factor of pi over 180, and we're not doing that. We're only using this. So, and again, they're not showing why this is true, but indeed it is true. Okay? d by dx of sine x is simply cosine x. d by dx of cosine x, however, is the negative of sine x. Okay? Now, should you be able to remember that, I will tell you what I use as my memory aid on that. The graph of the functions. Okay? Of course, I'm going to have to shrink this if I'm going to graph it, but let me get my pen colored correctly. If I can get it to come up, there it is. Okay. Would you agree with, okay, you tell me. Sine of 0 is what? I'm sorry? 0, very good. Our next key point is pi halves. What is sine of pi halves? 1. Okay? Pi, 0. 3 halves pi, negative 1. 2 pi, 0 again, and it goes on from there. Negative pi halves, negative 1, very good. Negative pi, 0 again. Negative pi halves, 3 halves pi, 1, very good. Negative 2 pi, and it goes on from there. So basically your sine function, I don't draw curves very well, but it goes like that, on and on and on. Now, you tell me, what does the first derivative represent? Slope of what? Tangent line. I wish I had drawn this a little bit better. Let me try doing better on this. Okay. Let me get that a little bit better. Okay. Well, depends on it. Okay, something like that. Now, what appears to be the slope of the tangent line at 0? That's a horizontal slope? Is that what you're telling me? I'm not. What appears to be the slope of that? Just make a wild guess. If I drew that anywhere close to true, what does that seem to be a line? Okay, it is a line. How could you characterize that line? What line does that look like it is? It's what? It's a tangent line. Yeah, that's what I drew it as. What function, what linear function would that line represent? Okay. What would it, I've already asked this, what seems to be the slope of that line? Okay. It looks like it's going up as much as it is going over, right? You go over this much, it goes up that much. What is that line called? That's a special name. You don't need to know the name. What if the line were like this? Do you think that could be a tangent line? For that? I don't think so. What would you tell me about that slope? big slope, little slope? Little. Okay. How about that one? Do you think that could be a tangent line? Well, that, I don't think so either. What would you tell me about that slope? Going up several for every little bit it goes over. Say again? A large slope. Larger than what? And this one less than what? Ah! And what would this line be? Slope of that line. 1! All right. Feel like a dentist. Okay. So let's just say that's the slope of 1. Okay? And that's at 0. Okay? At pi halves. What appears to be the slope at pi halves? 0. All right. That was much faster. And 0 is correct that time. Okay. Now, what appears to be the slope at pi? Oh, look at that. Yeah, -1. Okay. So that would be down here somewhere. What appears to be the slope at 3/2 pi? Oh, it's back up at 0. And what appears to be the slope at 2 pi? 1 again. Okay. How about at -pi halves? 0. How about at -pi? 1. That's the slope of 1. -1. I like that a little bit better. Okay. That'd be somewhere like right here. How about at -3/2 pi? 0 again. And at -2 pi? 1. Okay. Now what does that appear to be the graph of? You got it. A cosine function. Sort of. Okay, something like that. This goes down here, that goes down here. Okay. Would you agree that it appears to be derivative of sine is cosine? Would you? Okay. Now let's look at cosine function. What appears to be its derivative at 0? It's not going up. It's horizontal, right? Okay, this is cosine, okay? And it is, okay? So we started at a 0. That's fine. What appears to be the slope at pi halves? -1, okay? I'm going to change colors. What color would you like me to use? Red, okay? All right. So this will be 0 here, -1 there. Oops. Okay. How about the slope at pi for cosine? 0. How about at 3/2 pi? If I had gotten that through there right. 1. At 2 pi? 0. How about at -pi halves? 1. Oh, goodness, what happened there? Okay. At -pi, if I had drawn it right, 0. At -3/2 pi, -1. At -2 pi, 0. What does that appear to be the graph of? Exactly the opposite of sine, reflected across the y-axis. So sure enough, it appears to me, and it is true, the derivative of d by dx of sine x is cosine x, and d by dx of cosine x is minus sine. You see why it's true? At least figuratively, okay? Very good. Now, they do a proof of it, okay? And it's not a bad proof. Okay? And here's how it begins. D by dx of sine x, you know, the definition of the derivative is the limit as h approaches 0 of sine of x plus h minus sine of x over h. Remember that? Okay, let's expand that and see what we get. Does anyone remember, I'm going to write it over here, I'm going to go back to dark here, what the sine of x plus h is? Do you remember that sum angle formula? Oh, trig was so long ago, and I've already passed that course. I don't need to know it anymore, do I? If you have a doubt, look in your text. It's not exactly the front inside cover, but the next page. All right, you got it. What is it? Sine x. No, okay. Cosine h plus cosine x sine h. Very good. Excellent. Okay, so let's spell that out. The limit as h approaches 0 of sine x cosine h plus cosine, x sine h minus, that was all the first term, minus sine x divided by h, right? Now, what we're going to do next is gather together all the terms with x's in them and the terms with h's in them and see what we can do, okay? So these two have sine x's in them, so this will be, I'm going to leave off the limit because it's so messy to write. So this will be a sine x times cosine h minus 1, right? Plus cosine x times sine h, right? All divided by h. Okay? Now, what I'm going to do here, and this has the limits in here, remember, that would be, I think I'll write the limits in now, that because the next part really depends on it. So let me go and write them in. Okay. Again, this is the limit as h approaches 0. Now, notice sine x doesn't have an h in it, right? None h at all. So therefore we can pull it on the outside of the limit. It's just some value. So it'll be sine x times the limit of, as h approaches 0, of cosine h minus 1 over h. Plus, and we'll put another limit here, but pull out the cosine, cosine x times the limit as h approaches 0 of sine h over h. Okay? Now, I don't know if you remember this from earlier. Okay? Back in the limit chapter, that was chapter 1, no, chapter 2, okay, we had a couple of limits. Ooh. Boy, we don't have to go back there, I don't think. Let's just think this through, okay? Cosine h, as h approaches 0, goes to what? 1 minus 1 is? Over 0, so that's an indeterminate form. Now remember good old L'Hopital. Oh, we can't use that one, can we? Because yes, we can. Well, no, we can't, because that's what we're trying to prove. Okay, let's go back to the beginning of chapter 2. Okay? and this was stuck in there. I don't remember which section it was now, but we did these. One of those kind of a weird ones. Yeah. They probably tell us, and I didn't read. Let me look. Thought I could get there really quickly. Trigonometric limits, 2.6, okay? On page 90, chapter 2 limits, 2.6 trigonometric limits, important trigonometric limits. Do you see what the first one said? Theorem 2 there. The limit of, as theta approaches 0, of sine theta over theta is? You see it? It's on the left-hand side. Wait, are you in the new book or old book? New one, okay. Page 90. Theorem 2. You see it? What is this limit? 1. Okay. And what is the second part of that? Limit as theta approaches 0 of 1 minus cosine theta, which is the same as cosine theta minus 1, over theta. 0. So therefore, this says the limit is cosine x. So sure enough, the derivative of sine x is cosine x. Done all the way by the using those things we've already discovered. Okay? Now, we can do it also for cosine. Do you want to see that done, or are you happy with it? The book didn't do it, but I'll be glad to show it to you. What you think? Let me know. Yay or nay? You want to see it or not? Okay, I heard another head shake no. Okay, so let's move on to example 1. Okay, and by the way, let's see some other steps they may have done. Yeah, I hear they used boy, they skipped steps like crazy, didn't they? Wow. They went from this step to like 2 or 3 steps down the road here. And they got back to this. Then they did these limits like we did before, pulling out that. This one goes to 0, that goes to 1. So that just left them with cosine x. Okay? All right. That looks like graphical insight. So what I take it then is we don't have a slide for example 1. So let's erase all the ink and use this. Calculate f double prime of x, where f of x, this is what we're looking for, when f of x is equal to x cosine x. Boy, they jump right in there, don't they? Okay? Now, when you look at this function here, what pops out at you first thing? It's a product of 2 functions, x times cosine. And by the way, the question I was looking for earlier, the function f of x equal x, is called the identity function, and that has a slope of 1. Okay? But that was earlier. Don't worry about it now. Okay, how does the product rule go? You got to do f prime of x before you can do f double prime. So what would that be? How does product rule go? Someone remind me. Derivative first, which is? Now derivative of x is 1, okay, times cosine x, times the second, right? plus, I'll put the plus for now, what? Okay, the first times the root of the second. What's the root of cosine x? You didn't want me to prove it, but you said you believed me, huh? Derivative of cosine x? Negative sine x. So that makes the plus become a minus. Okay, and that would be sine x. Very good. Now let's do f double prime of x. That's what we're looking for. And what would that be? What's the derivative of cosine x? You just answered it. Negative sine x. Okay, and then what do we have? Another x sine x. How do we calculate that? You just answered it a little bit ago, at the very beginning. Product rule. Product rule. And how does the product rule go? Help me, help me. How does the product rule go? Derivative of the first, which is 1, times the second, which is minus sine x. Plus, except we got a minus in front, what? Help me, help me. Okay, you got an x, the first, times the root of the second, which is cosine x. Okay, can you clean that up just a little bit? Combine like terms. Negative 2 sine x minus x cosine x. All right, let's see how the book did. Yep. Negative 2 sine x minus x cosine x. Good for them. All right. Now, the next, any questions on that before I leave it? Remember how to do product rule? Does this make sense? Okay. All right. This graphical insight is exactly what we did before. That was my visual on how to remember this. Okay? They're only doing the zero tangent lines, but they should be able to do this too. This is the graph of y is equal to sine x, the blue curve, and then picking out the horizontal points, that would be first derivative is 0 there, there, and there. Okay? First derivative there appears to be 1, so we put it there. First derivative there appears to be minus 1, so we put it there, and go on. Again, it looks to be 1 there, minus 1 there. So sure enough, we have the cosine. If y is equal to sine x, y prime is cosine x. And then you can turn that around. I probably should have blown that up. But that's the same thing we did earlier. Okay? Only maybe a little prettier. I don't think it's very much prettier. Do you? You better say no. Okay. But there's the graph. And it only shows one way. But then you can turn around and do the same thing. Root is here, and here, and here, and here are 0. Okay, those zeros are there. And then this is a plus 1 here, a minus 1 there, and a plus 1 there. And sure enough, you've got your opposite of the sine x. The root of cosine x is minus sine x. Okay. Same thing we did before. Now, the derivative of the other standard trigonometric functions can be computed using the quotient rule. Okay? Do you want to see one of those, or do you want to just take its word for it? Not that hard to do, but what you want. You want to just take their word for it or see them? See why. Say again? Take your word for it? Boy, he's easy, isn't he? Okay. Okay, here are the other rules. If anyone wants to see it, they're not that hard to do. Just using quotient rule. I don't like the quotient rule that much, but just to get you, if you wanted to do this, write this as sine over cosine, right? And then use the quotient rule on that. And sure enough, you're going to wind up with secant squared. You're going to wind up with 1 over cosine squared, and that's going to be secant squared. And if you did this one, you'll get minus cosecant squared. That one, strangely enough, now this quotient rule is 1 over cosine. So that's going to be a little, and you would think that'd be easier than this or simpler. It actually comes out rather bizarre, but it is still true. The derivative of secant is the product of secant times tangent, and the derivative of cosecant is minus cosecant times cotangent. Okay? You don't want to see any of those done, or if you do, let me know. They're not that hard to do. But no? Yay? I heard a no, but we'll go on if you don't want to. All right. Oh, ho, ho, ho. Example 2 says verify the first one. Okay? So you can't get out of it. Okay? So here is going to be verify this formula that d by dx of tangent x is equal to secant squared x. Okay, we're going to have to do the quotient rule. So this is d by dx of, what is tangent? It's what? Okay, sine x over cosine x. Okay? And by the quotient rule, what would that be? Remember the quotient rule? Anybody? You don't even remember my little sing-songy thing for it, huh? Low d high minus high d low over low low. Remember that? Start low and work up. Okay, low d high. Low is cosine x. What's the derivative of sine x? Anybody? We just did it. Derivative of sine x? Cosine x minus what's the rest of the quotient rule? I just said it for you. High d low, high is sine x. And what's the derivative of cosine x? Negative sine x. Over, what was the last of the little song? Cosine squared, or low, okay? It's cosine squared x. All right. Well, what's cosine x times cosine x? That's not that hard. Cosine squared x. Perfect. And then you got a minus times a minus. That gives you a plus. And sine x times sine x is not that hard. Sine squared x over cosine squared x. Well, what's cosine squared plus sine squared? 1. So this is the same as 1 over cosine squared x. And what is 1 over cosine squared x? Secant squared x. You got it. So we just did prove that. Sure enough. I told you it wasn't hard. Now, graphically, is that really all that easy to see graphically? May or may not be. I'll let you decide. Here is the graph of tangent x. Okay? There's vertical asymptotes at every half pi. Okay? So therefore, tangent is not defined at the half pi's. Why? Because that's where cosine is 0. So you can't have it. So secant can't be, well, wait, we'll get there. Okay? The derivative can't be defined at the half pi's either. We'll put it that way. All right. What appears to be the derivative of tangent there at 0? What seems to be the derivative of tangent at 0? What's the slope of the tangent line there look like it is? Right at 0. What does the slope of the tangent line appear to be? 1. Exactly. So we'll put a 1 down there. Okay? Now, if you get close to minus pi halves, that slope is getting close to being vertical, which is undefined, of course. But it's a very large, very positive slope, but it reduces and goes to 1 here, but then slowly increases and goes very large again, always positive. So it starts at positive infinity. It doesn't ever reach negative pi halves. It starts at negative infinity, comes down, and then gradually loops back up and goes like that. And then and by the way, just a little refresher, the secant function looks something like this. That's secant squared. Here is secant. It comes down like this and goes up like this, approaching infinity. But down here, it'd be a minus 1, in doing that. But when you square it, then it flattens out some here, it gets steeper there, okay? So, but here, all the negatives become positive, so it flops back up there. And sure enough, it just repeats itself over and over and over. So there it does look like, that's not as familiar to you, I'm sure, as sine and cosine, but that does look like secant squared. I don't know if you find that helpful or not. I don't. I just remember derivative of tangent of secant squared. Okay? You don't use it that frequently, it's just remember it. And if you don't remember it, look it up. It's in the front of your book. Well, probably in the back of your book. Okay? Under derivatives. Okay. So let's do example 3. Hi, here's what 1 was wanting to do earlier. So you finally got your wish. Oh, wait, that's not what I want to do. Okay. It says find the tangent line to the graph of y is equal to tangent theta secant theta. Y is equal to tangent theta secant theta at theta equal pi fourths. We want find the tangent line. Now, how do we find the tangent line? We've only done it several times, but how do we find the tangent line? What do we need? One was trying to give it to me earlier. Say again?
The y-slope formula?
The point slope formula, was that what you said? I thought it was, okay. All right, how does that go? Okay, got it. Okay. Now, you tell me what your y1 and x1s are. Except now we don't have x's, do we? What do we have in this problem? Thetas. And that takes the place of x. Oops, it didn't do it. Okay. So those are theta 1s now. whoops, and that's a theta too, isn't it? Okay. Now, ooh, boy, did I botch that up. This is still y1. Okay. So, okay. Now, do we know any of those? Okay. Our thetas and y's are your variables, right? So don't mess with theta and y. What we're looking for, y1, m, and theta 1, we need numbers there. Okay? Which one of those three numbers do we know already? Second? Theta 1. What is theta 1? Pi fourths. Yeah, that's what that is. That's the thing we know already. So now we know that y minus y1 is equal to m times theta minus pi fourths. Okay. Now, how do we get either y1 or m? I don't care which one you choose. Okay, which one does that give you? M, okay. We get the m by taking a derivative of y, okay? So what is y prime? Whoops! What kind of rule do we need here? The what product rule, and how does that go? Derivative of tangent is what? Derivative of tangent is what? Secant squared times secant theta times the second plus tangent theta, the first, times anybody? Help me. What's the derivative of secant theta? It's been a long time, I know. At least 15 minutes. What's the derivative of secant? Say again? Secant theta, tangent theta, is that what you said? Okay. Secant theta, tangent theta. Okay. So we could, if you want to, combine a few things, and that would be secant cubed theta, not that this is really all that helpful, plus tangent theta times, no, tangent squared theta times secant theta. Which you could write as secant theta, because that's common to both terms, times secant squared theta plus tangent squared theta. I'm not sure that's helpful, but you could write it that way. Okay? Now, that would be for any value theta. We're really interested in the slope where? Theta equal pi fourths. So do we happen to know what secant theta is at pi fourths? Anybody know? Secant of pi fourths. Tell me what secant is anyway, in terms of sines and cosines. Yeah, what about it? Is it equal to cosine? 1 over cosine. Right? Reciprocal. 1 over cosine. And we're interested in pi fourths. Okay? Now we can do the same thing here. That'd be 1 over cosine squared at pi fourths. Plus, now, does anyone happen to know what tangent of pi fourths is? I was hoping you did, but if you don't, that's fine. What can we write that as? What is tangent? Second? Okay. Yeah, okay, so this will be sine squared of pi fourths over cosine squared of pi fourths. Now all this is worthless unless we know what cosine and sine of pi fourths are. What is cosine of pi fourths? Does anyone know? Oh, I'm not going to tell you, trig teachers. Huh? Root 2 over 2. So this will be, I'm going to write that slightly differently, 1 over root 2. Isn't that the same as root 2 over 2? Okay. And this will be times 1 over root 2 squared plus, anyone remember what sine of pi fourths is? Yes, it's also root 2 over 2. So that would be 1 over root 2 squared over 1 over root 2 squared. Do you buy that? Well, 1 over root 2 is? You know that. Dividing fraction forms, 1 divided by 1 over root 2. That's the same as 1 times root 2 over 1, right? That's why I wrote it this way. That's root 2. And what would that be? 2 plus 1. All right? So that'd be 3 root 2. That's what the tangent at, that's what derivative is at pi fourths, 3 root 2. Okay? You buy that. So that's what your m is. So now we have y minus y1 is equal to 3 root 2 times theta minus pi fourths. Okay? We still need to know what that y1 is. How in the world do we get that? Plug it in your y. Yes, exactly. So y1 is equal to tangent at pi fourths times secant at pi fourths. Does anyone remember what tangent at pi fourths is?
Oh.
1, exactly. Okay. How about secant at pi fourths? Root 2. So that would be 1 times root 2. So that's just going to be root 2. So now we have y minus root 2 is equal to 3 root 2 times theta minus pi fourths. And it is an ugly looking equation, but that's what it is. Okay. I really don't see an advantage in writing in slope-intercept form. I'm really happy leaving it in that form. What does the book do? Yes, thank you so much. It leaves it in that form. Y minus root 2 is equal to 3 root 2 times theta minus pi fourths. Because if you try to write it in slope-intercept form, you got 3 root 2 times theta. That's no problem. Minus 3 root 2 pi over 4. What a mess, okay? And then you have to subtract this or add that to both sides, and it really gets messy, okay? This is the simplest form to do that in. And that's what they did. All right. Now, let's just play around with this a little bit. 3 times root 2. Root 2 is something like 1.414. So 3 times 1.4, let's just round it to that, would be about 4.2, I believe it is. Okay? Approximately. that's going to be the slope. Now, here's the problem here. Look at what they've done. This is approximately 3/4, right? Pi is 3.14 over 4. That would be about 3/4. So that's 3/4, but that's almost 5 here. So they haven't drawn the scale on the same scale, okay? So they've got the y compressed and the x expanded, so you really can't tell your slopes too well. Except it is going to be a negative slope, and I think you can see that when you multiply this by that, you get a minus number, and then you add a smaller minus number to that, it's still going to be minus. And the slope here, and again, you can't tell that by looking at it, but it's a positive slope going through there, intersecting there. You can't do much better than that. I can't even draw that curve very well. I would have to use a graphing calculator to do that anyway. But if you did plug those values in, you'd find out that would be a tangent at that. I really like they give you such simple problems to start with, don't you? Okay. But it's doable. All right, so there's example 3. And guess what, folks? That's all of 3/6. That's it. Okay? Now, do you find these preliminary questions, you want to do some of those or not? Yay or nay? You tell me. Yes or no? Huh? No? Okay. Homework exercises then are either 1 or 3 or both. Okay? Sort of similar to what we just did, only maybe a little easier. And then any of the odds 5 through 23. And then any of the odds 25 through 33. Either 35 or 37 or both. Either 39 or 41 or both. And then any of the odds 43 through 51. Now, some of those say that they require graphing utilities. I'll let you figure out whether you need that or not. And one of them, it says, is a writing thing, so you just have to think through that answer. There's not really a lot of math to do in it, except conceptual. Okay, and then you can look at any of the odds on the further insights and challenges. Any questions on that? If not, this is from the summary, again repeating the first that we had, which really you need to know, okay? These are ones that you use so frequently, you really need to know those. You can look them up if you forget them, by all means do so, but you really need to know that. Derivative of sine is cosine, derivative of cosine is minus sine, okay? Once you get into integrating, which is next term, you're going to need to know those, okay? And that is all for 3.6. That was pretty quick, right? So let's move on to 3.7. Some of you were concerned we weren't moving fast enough in Chapter 3. There's a lot of sections, but quite a few of them are fairly short, or a few are. 3.6, very short. Okay. Let's start this at the current slide. And before we hit what the chain rule is, what if you had a function like this? And believe me, you will have functions like this. Y is equal to cosine of x squared. Now, certainly that's different from cosine squared x, cosine of x squared. Right now, we don't have a tool in our toolbox to do that. That's not a product function. That's a function of a function, the cosine of the squaring function. Now, phrasing it that way, that's cosine of x squared. You remember back from, I assume, did most of you have pre-calculus at some point? You did, okay. either in high school or in college, okay? In pre-calculus, what was it when you had a function of a function? Think f of g of x. What do we call those? Composite functions. And you may have wondered, why in the world do we need to know that? Is that just some other piece of stuff they came up with for us to deal with? No, there's a reason that you dealt with composite functions, because the chain rule comes from that. How about this? Y is equal to the square root of x fourth plus 1. Well, if that was x plus 1, I think I could do that one. But x fourth plus 1, again, you have a composite function. The square root of another function, okay? So we know the rules for taking derivatives of sums, derivatives of differences, derivatives of products, the product rule, derivatives of quotients, the quotient rule, but we don't have the derivative of a composite function, okay? And that's what the chain rule does for us, okay? Now, they give you this thing about composite function, just to remind you, when you do f of g of x, okay, that can be written as f circle g of x. That's the definition of a composite function, okay? A function of a function, okay? Now, they threw that notation in. We seldom use that notation. But that's exactly what those two are. In this case, your f was the cosine function, your g was the x squared function. In the second case, your f was the square root function, your g was the coordinate function plus 1, x fourth plus 1. That's what you would be doing with that. Now, they actually gave it the other way. We call f the outside function and g the inside function. Often we write composite function as f of u, where u is g of x. That's another way you could do it. So, what we do with that, if you use that notation, this y is equal to cosine of x squared, that would be y is equal to, if u is equal to x squared, then this would be y is equal to cosine u. Okay? And on the second one, the u would be x fourth plus 1, and then this would be y is equal to the square root of u. Okay? If that helps you see it and think through it, fine, go for it. Okay? So that then leads us to the chain rule. Now, I noticed somebody got up. Let's see, we're about an hour and 15 minutes, right, into the class. And we've still got another hour and more than 15 minutes left. Do you need a bladder break now, or you want to wait and take it later? Huh? Wait? Okay. Is that okay? So she left. I was going to take advantage of that if you wanted to. So here is the chain rule. That's what we call it when you're taking the derivative of a composite function. Now here's the requirements. Both f and g have to be differentiable. Okay? Now, what we really need to say on some interval. Okay? But that gets a little more complicated, but they just have to be different. Then the composite function, f composed of g of f, which is f of g of x, is differentiable. Also, if both of these are differentiable, then the composite function is differentiable. And here's what its derivative is. You're taking the derivative of this composite function. How do you do it? You take the derivative of the outer function, evaluated at g of x, then you take the derivative of the inner function, g prime of x. So it is a product, just like, well, this isn't a product, but it's the derivative of the outer, evaluated at the inner, then multiplied by the derivative of the inner. Now, a lot of people, and it's perfectly fine to do so, will put the g prime in front and then the F prime of G afterwards. That's fine. But just remember, you've got to do both steps. Okay? It results in a product, but it's not a product rule. Okay? Any questions on that? So let's do example 1. And I don't think example 1 has a slide. So we'll clear the ink on this one and go for that. Calculate the derivative of y is equal to cosine of x cubed. Okay? Anyone want to hazard a guess on what the derivative of that would be? Anyone? Okay. Now you're starting with, okay, there's really no way you're going to get a cosine. What did the rule say? Take derivative of the outer function. Derivative of, okay, start over. Which is the outer function, which is the inner function here? X cubed is inner. It's inside, yeah, and cosine is outer. So it says take the derivative of the outer. And what's the derivative of the outer? Derivative of cosine? Negative sine of x cubed. Okay, leave the x cubed alone. Then you do derivative of the inner, which is 3x squared. Okay? Now you see sort of the reason people tend to put the g prime first, except it's not completely first. I put the sign first, then I put the number 3, then I put the variable x squared, then sine of x cubed. Now, that's how I do it, because I don't want to be confused that this times 3x squared is multiplied by that. It is not. That's multiplied by the whole thing. So if I put it out front, except I want to keep the minus out front, minus 3x squared times sine of x cubed. Like I said, this is a product here, so you can multiply them in any order you want to. The minus first, the 3x squared, sine of x cubed. That way there's no ambiguity that things are multiplied, not this is multiplied by that. Okay? Let's see what they got. Yes, minus 3x squared sine of x cubed. Got it? Ready for example 2? Yay or nay? Is anyone with me? Okay. Let's do example 2. Find derivative of y is equal to the square root of x fourth plus 1. I've seen that one before. Now, time out, folks. When I'm taking a derivative and later integrating, I very seldom, if ever, want to use a radical sign. Generally, I want to rewrite that radical in terms of exponents. So that's how I would suggest starting this problem. What would be another way of writing that? What does a radical mean? Huh? No, it's square root. But what does that, how do you write that as an exponent? Ah, yes. That would be x fourth plus 1 to the 1/2 power. Does everybody see that? Okay? Now the next question is, what's the outer function, what's the inner function? You can look at it in either form, and you should be able to tell what you reckon the inner and outer is there. Make a guess. Okay, the inner is x fourth plus 1. Is that what you said? Perfect. The inner is x fourth plus 1, either in the first one or in the second, and the outer is the square root function, or raised to the 1/2. So what you want to do first? Y prime would then be okay. I wouldn't use the square root. I would use the power form. 1/2. Okay. Someone else would give me the derivative of g first. That's fine. Derivative of inner first. But what was it? So someone say 1/2 first. 1/2. Now x fourth. Keep it at that value. G of x. X fourth plus 1 to the negative 1/2, right? You subtract the power by 1. Then you do the derivative of the inner function, unless you did that first, which you were starting to do, which would be perfectly fine. And what would that be? 4x cubed, exactly. Okay, now before I do anything else, I notice that the 2 will go into 4 2 times. Okay? Now the minus 1/2 means that's in the denominator. So the only thing left in the numerator is 2x cubed over, and then let's get it back in radical form. That would be the square root of x fourth plus 1. Okay? Do you buy that? Chain rule. The derivative of the outer evaluated at the inner times the derivative of the inner. Okay? Then the rest of it is just algebra, having to rearrange it. So that gives you, and I can't believe they did that. They left the 4 and the 2 in there. It makes no sense. Divide the 2 and the 4 and you get 2x cubed over the square root of x fourth plus 1. Now, as I said, when I'm taking derivatives and later when I'm integrating, I will always get it in power notation, exponential notation, rather than radicals. But when they give you the problem in radicals to begin with, usually they won't be answering radicals. So that's why I went back to radicals there. It was perfectly okay if you wanted to write that just like it was before. 2x cubed times x fourth plus 1 to the minus 1/2, that would have been fine. Or 2x cubed over x fourth plus 1 to the 1/2, that would have been fine. But since the original problem with radicals, I've brought it back as radicals. And that's usually how the book does it too. Okay? Any questions on that? All right. You see in chain rule? They're going to come up with another doozy. Let's see what they got. Example 3. Calculate dy dx when y is equal to the tangent of x over x plus 1. It's a pretty ugly x. Let me write that better. Okay. My eyes are hurting. Did yard work yesterday, and I think I got something in them, and they're really stinging. But okay. How would you approach this? What kind of function is that? Say again? Okay, not quite. Are you saying you're multiplying tangent times x over x plus 1? No. X over x plus 1 is the argument of tangent. That's what you're taking the tangent of. So this is a, okay, the inner part is a quotient. It does have an outer part, tangent. That makes it a composite function. Tangent being the outer part, the quotient being the inner part. So therefore, in order to do this, you've got to use the chain rule and the quotient rule. Okay? So How do you eat a 5,000-pound elephant? One bite at a time. Okay? So just take a step at a time. Let's start with the composite function. How would that go here? Now they call it dy dx, which is the same as y prime, but dy dx is what? I'm going to write this out in a little more detail than I usually do. That would be d by dx of tangent of x over x plus 1 times d by dx of x over x plus 1. Do you buy that? In other words, it's derivative of the outer function, tangent, evaluated at x over x plus 1, then times the derivative of x over x plus 1. Make sense? That's the chain rule, right? Now, what is the derivative of a tangent? It's been a while. Secant squared. So this part would be secant squared of x over x plus 1. That's all you have to do to it. Just take the derivative of the outer function. But here on the inner function, you got to take its derivative. And what was that? How do you do, and what kind of rule is that? Quotient rule. And how does quotient rule go? Second? Okay, yeah, low, which is x plus 1 times the derivative of the top, d high, which is 1, minus how's the rest of it go? High, which is x, d low, what's the derivative of the denominator? 1, okay, that's good, over x plus 1 squared. Very good. All right, now, that numerator is pretty simple. X plus 1, because those parentheses really aren't doing you any good here, so I'm going to erase them. X plus 1 minus x. What does that come out being? 1, okay? So that last part is just 1 over x plus 1 squared, okay? So let's rewrite our thing, because I'll sort of, if you left it like that, you might be tempted to think that's just multiplied there. It's not. It's that, and this is why some people do the g prime in front. This will be 1 over x plus 1 squared times secant squared of x over x plus 1. You see, if you wrote this over here, you might be tempted to multiply those and take the secant squared. No, that's not what it is. It's the same times that. So that's why I like to write it that way, and that's why a lot of people do the g prime in front, because quite often it makes more sense to put it there. But that's our answer. Let's see how the book did. Boy, why would they ever write it the way they did? I think our way is a lot neater, but they write secant squared of x over x plus 1 divided by your denominator, which is x plus 1 squared. That's a perfectly good way to do it, but I never would have done it that way. That, to me, is so much simpler. Okay. Now, example 4 is a kind of real-life type problem. Okay? Can you do those? Sure you can. You better be able to. The daily natural gas usage in a household follows a pattern given by capital G of T, which I assume is gas usage as a function of time, is equal to 300 times 1 plus cosine of 2 pi t over 365. Okay. Now I put the 2 pi t over 365 in parentheses, the book didn't. I think it's far simpler to put that there. That's cubic feet per day, okay? Where t equal 1 corresponds to January the 1st, assuming that it's not leap year, find the rate of change of usage on March 1st, June 1st, September 1st, and December 1st, okay? Now, what in the world are they saying here? This is just, notice, cosine of 2 pi would refer to an entire one cycle, right, of the cosine function, right? Starting at 1, going down, coming back up, okay? Now, if you make that whole year one cycle, which is exactly what they've done, if t is in days and you're dividing by 365, you're making that one cycle. In January 1st is going to be some of the coldest weather you've got, right? So that's when you're going to use your natural gas the most. And then it's going to go down like this and bottom out around June 1st. Right? I mean, July 1st is going to be the warmest time when you probably use the least natural gas. And then as the fall comes on, you go back up. And December 1st is probably not usually the coldest, but that's a fair assumption, right? That's a pretty good illustration of how you're using natural gas. Now, the one big difference here is that it's not just that function. You're multiplying 300 times it, which is going to raise it up, elevate it 300 this way, and then you're going plus or minus from there. So that takes out all your negatives. 1 plus cosine is going to get this graph to be up here. So this is going to bottom out at 0 at July 1st or somewhere around there. Okay? So it's always going to be positive. You won't have any negative times where you're paying back gas. No, you're not. So that's what that does. And 300 is just a multiplier. Okay? So there's your function. Okay? That's cubic feet per day. Okay? Find the rate of change. Okay, now this is the daily natural gas usage in a household follows the pattern given by this. It says, assuming it's not a leap year, find the rate of change. And what does rate of change mean? What does rate of change mean? That's one of those questions. A good answer for most questions would be, especially in Cal 1, take a derivative, exactly. So the rate of change would be dg dt, the time rate of change of g. So let's take that, okay? Now, before I did this, I think I'd multiply on through and make this 300 plus 300 cosine of 2 pi t over 365. Okay? Now I would take a derivative of that. That's a little bit easier. What's the derivative of 300? 0. Very good. Then 300, that's just a constant, times the derivative of cosine, which would be derivative of cosine, hasn't been that long, negative sine of 2 pi t over 365. Are we through? Nope. Chain rule. Got to take the derivative of the innermost function. What's it? With respect to t. It's real easy. It'd be 2 pi over 365. It's just a constant times a t. The derivative of a constant times t is just that constant. Okay? So I'm going to clean this up a little bit and rewrite this as minus 600 pi over 365. And frankly, I would divide out at least by 5 there. Sine of 2 pi t over 365. Okay? Now it wants the time rate of change of using this on, what is it? March 1st, June 1st, and September 1st and December 1st. So that's 4 dates. Now, the reason they said the thing about the leap year, assuming it's not a leap year, what we have to do where t is the day of the year. I don't know if any of you are familiar with that. They sometimes call it the Julian day. In other words, how many days into the year. So on March 1st, you got to figure out how many days into the year you are. How many days has January? 31. February? No, it said not a leap year. 28. Okay. So 31 and 28 are 59. And March 1st would be the 60th day. So that would be 60. So you plug in 60. So dg of 60 dt would be minus 600 pi over 365 times the sine of 2 pi times, what did I say, 60 over 365, which would be minus 600 pi over 365 times the sine of 120 pi over 365. Okay. Someone with a calculator, what mode had you better be in? Radian mode. So in radian mode, calculate what that is. Second. Negative 4.4. And that would be in cubic feet per day squared is really what it would be, but that's a rather strange unit. Okay, and they took it more digits, but I think you're right to do negative 4.4. What does that mean? That on March the 1st, you're probably using about 4.5 cubic feet less a day than you did on the 28th of February, because the days in general are warming up. And that's one of the times of years when they're usually warming up pretty quickly. Okay? So let's do the same thing for June 1st. Okay? June 1st is what Julian date? Well, again, January is 31. February is 28, not a leap year. March is, anyone know? 31. April is? Y'all want to know the easy way to do this? Ball up your fist, okay? Start here. January, February, March, April, May, June. January, February, March, April, May, June, July. Okay? The ones on the knuckles are 31. The ones in between the knuckles are less than 31. February is 28, the rest are 30s. Okay? That's an easy way to do it. Okay? Then when you start over with August, you start back on the knuckle, because July and August are both 31. September, October, November, December. Okay. So make a fist. Okay. Power. Okay, never mind. Okay, so it'd be 31, 28. Okay, so this is January, February, March, April. May would be what? 31. And then June 1st would be one more day. So let's add those together. That's 8, 9, 10, 11, and 1 is 12. And then you have 3, 6, 9, 12, 15. It's the 152nd day of the year. So your G prime of 152 would be minus 600 pi over 365. That stays the same. Times the sine of 2 times 152 would be 304 pi over 365. Okay, so that's what you figure for June 1st. You tell me, you think it's going to be a positive or negative number? I think it's going to be -2 because it's getting cooler. I mean, it's getting warmer every day, so you'd be using more natural gas, less natural gas every day. Anyone got it plugged in yet? But I'm guessing the temperature isn't changing as fast as it was back in March 1st, because by June it's sort of leveling out, so I think it would be a smaller negative number. What do you get? Anybody? -2.5 approximately. And that would be cubic feet per day squared. That's a weird unit. They don't usually give the units. They get 2.6, -2.6. They rounded, right? Okay, September 1st. Okay, we already did April, May. Ooh, don't do that. This was May. June was how many? 30. July, 31. August, 31. And then September will be one more. So let's add those up. 8, 9, 10, 11, 12, 13, 14. So that's a 4. Carry 1, 1, 2, 3, 4, 5, 6, 7, 8. That's 164 approximately. So this time we'll do, I'm going to write it up here, -600 pi over 365 times the sine of, and this is 2 times that, which would be 328 over 365. Is that right? Yeah, I guess so. Okay, you punch the numbers now. On September 1st, what you reckon is happening? Yeah, it should be a positive number because it's now getting a little cooler every day on average. Okay? So we're hoping this is flipped positive, but probably not too positive. I'm guessing maybe 3 or something like that. What do they get? Oh, no, more than that. Anyone punched it in yet? $4.5, and that's about what they get. Approximately 4.5. And again, cubic feet per day. On a positive now, because you're using a bit more. December 1st, you see the pattern? Do you need to do any more? Count your days and do, they got a positive 2.55, 2.6. Okay. Now, let's rewrite the chain rule, they suggest, in, I'm sorry, I'm in the wrong thing. Let me erase what I've got here. And they suggest writing it in Leibniz notation, which would be here's what you start with. Y is equal to some function of u, which is function of g of x, where u is equal to g of x. Okay? Then your dy dx is equal to df dx times the I'm sorry. If you're doing this with u, then that would be df du, but then you do a du dx. Okay? Remember, u is equal, u is equal to g of x. That's the assumption here. U is equal to g of x. And that's exactly what we have down here. The f du, keeping this is u, then du dx, which is that last part. And sure enough, it looks like, but it's not doing it, that the du's are canceling out. It's not. They don't cancel out, but that gives you a sort of a nice warm and fuzzy that you are doing it right. I don't think that makes me feel any warmer and fuzzier, but the book thought you would, okay? And that then gives you that next little thing they have, dy dx is equal to y du dx, okay? They don't write that down here. They go straight to Christian Huygens, who was a Dutch, I believe, one of the most famous scientist of his day. He was Leibniz's teacher in mathematics and physics, so he had to have been a pretty good dude, okay? He admired Isaac Newton greatly, but did not accept Newton's theory of gravitation. He referred to it as the improbable principle of attraction, but he was totally wrong, okay? Because it did not explain how two masses separated at a distance could influence each other. Why they put that in here, I'm not really sure, okay? Of course, back then, they didn't understand force at a distance, or, goodness, in physics you call that non-contact forces. Sure, when I hit the desk, it hits me, that's a contact force. But a force that's acting at a distance is called a field force. The fields interact. And Huygens, of course, couldn't buy that at all. Now, why did they put that in here? I'm not sure. Except he was Leibniz's teacher. So here's Huygens. If you want to write on Huygens, you certainly can. They have a little conceptual insight here, which it maybe is something that makes a lot of sense to you. I mean, it's the thing we just did. But their example, d by dt of your salary is D by your salary to your friend's salary times D of your friend's salary to DT. I guess if you make twice as much as him, yeah. Which I guess is all well and good. It just seems like a pretty, it's a good example. I'll just leave it like that. But it doesn't help me any, but it's a good example. All right. It looks like we do example 5 before we move to theorem 2. Imagine a sphere whose radius r increases at the rate of 3 centimeters per second. Okay. Is it better to write over here? We probably have more room here. Okay. I don't draw spheres very well. You get a picture of that being a sphere. Pretty ugly sphere, but you got it. It's a ball, okay? Now, here's the radius of that sphere, r, okay? Now, this sphere is growing, and it says, whose radius r increases at the rate of 3 centimeters per second. How would I write that mathematically without writing all those words? The sphere increases at a rate. How would I write that mathematically? Second? Delta? Actually, now we're doing derivatives, so let's use d. So I think that you're right on the money there. dr dt is equal to 3 centimeters per second. Okay? Now notice here, folks, units are your friends. Okay? Certainly you measure a radius in a length measurement, such as centimeters, right? If this was a soccer ball, a basketball, even a tennis ball, you would not want to use meters, you would use something like centimeters. And if the radius was changing, let's imagine this is a balloon, a perfectly spherical balloon, and you're blowing it up. When you're blowing it up, so the radius is increasing plus 3 centimeters a second. R is a radius, T is time, centimeters per second. See, your units even are helpful to you. That's your dr dt. Okay? At what rate is the volume of the sphere increasing? What we're looking for is then what? At what rate is the volume increasing? What is going to answer that question? dv dt. At what rate is the volume? When you see rate, think of dividing a derivative with respect to time. This is what we're looking for. Okay? Everybody buy that? Okay. At what rate is the volume increasing when r is equal to 10? 10 centimeters. And here's Jasmine. All right. We're winding up only missing now Tia. I believe it's the only one we're missing because we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of 1, 2, 3, 4. Yeah, 10 out of 11. Way to go. Very close to perfect attendance. How would you do this? There's your setup. The rate at which the radius is increasing, dr dt, is 3 centimeters per second. What is the rate at which the volume is increasing? That's dv dt when r is equal to 10 centimeters. So you're blowing up this balloon, and when you've reached the 10 centimeters, but you're still blowing, and it's going to increase at 3 centimeters per second, at what rate will the volume? In other words, how much air are you having to pump into that thing? Now, if I'm not mistaken, this is your 10 o'clock Wednesday, 1st of the month. So that's not a weather. It is a weather alarm, but it's a test, okay? How would you do this? What must you know in order to answer that question? Don't you see you've got two functions there? The radius function and the volume function. Do you have some way to relate those two together? In other words, form a composite. How does radius relate to volume, or volume relate to radius for a sphere? Anyone happen to know that? If you don't, open your text, not to the first inside cover, but to the next inside cover, and what do you see? Bottom of the page. The previous page, that one. Under geometry. Not area, they're asking for volume. V is equal to 4/3. Go on. Cubed. All right. Feel like a dentist. So V is equal to 4/3 pi r cubed. And guess what we're going to do? Second. I can't hear. Not plug it in. You got to get to this. What does that say? But it's one of those questions. Take a derivative, okay? Except this derivative is going to be dv dr. Okay? You're looking for dv dt, but let's do dv dr first. And what would that be? Anybody? Oh, pi is certainly there. Second? Okay. R squared is certainly there. 3 times 4/3 is 4. 4 pi r, I said squared and wrote a cube. Sorry about that. You said it right. I said it right, but I wrote it wrong. There's your derivative with respect to r. But we're looking for dv dt. Well, by what we did just a little bit ago, dv dt is dv dr times what? dr dt, right? And then it looks like the r's cancel out. They don't really. So this will be 4/3 pi, 4 pi r squared is what I'm trying to write. That's dv dr is 4 pi r squared times dr dt is 3. Okay? And we're looking for dv dt when t is equal to, when r is equal to 10 centimeters. Okay? Well, that would be 4 pi times 10. Second? Squared, 10 centimeters squared times 3. So that will be 1200, because 10 squared, pi square centimeters. No, cubic centimeters. Bless you. Okay, cubic centimeters per second, because the 3 has with it centimeters per second. I forgot to write my units down. Shame on me. So you have centimeters squared times centimeters per second would be centimeter cubed per second. So the volume is increasing at a rate of 1200 pi cubic centimeters per second. You're having to blow a lot of air in there really fast. Okay? At 10 centimeters, you're really huffing and puffing to blow the house down. Okay. Does that make sense? And that's a great unit for volume per time, cubic centimeters per second. Units are your friends. Okay? Let's see what they got. 1200 pi, and they multiplied that out and got something like about 3,770 cubic centimeters a second. Okay? I'm about ready for a bladder break. Can any of you take one? Okay. Let me pause this. I can't talk either. I'm throat. All right. Now, that leads up to discuss some important special cases of the chain rule. Oh. Okay. Probably shouldn't have left that writing there, but I don't think it's going to hurt too badly. If g of x is differentiable, of course it had to be, then d by dx of g of x raised to the nth power. Now that's not x raised to the nth power, but the whole function raised to the nth power. I would have put the n over here, okay? But they do it this way. Then that would be n d by dx of power function would be n times g of x to the n minus 1. That's the derivative of the power function. So that's your outer function. Then by g prime. And that's good for any number n. Now notice they didn't have in here an f at all. F is your power function, and the power function is differentiable everywhere. Okay? So this is derivative anywhere. Okay? Now, how about this one? D by dx of e to the g of x. Now which function is which here? Which is inner, which is outer? That's a composite function, by the way. Which is inner, which is outer? The e to the x is the outer function, and g of x is the inner function. So that would be, now they write this in front here, and there's a good reason for it. G prime, they're doing in front first, e to the g of x. So it's just another. This is your power function, this is your exponential function. And they basically, even though they write the order differently, it goes the same way. You take the derivative of the outer times, derivative of the power function in g of x into minus 1 times the derivative of the inner function. Here you take the derivative of the e's, which is e to the g of x, times the derivative of g prime of x. They just write the g prime in front, which I think is better anyway. Okay? So those are just two special case examples. I don't know why they did a separate theorem for them. Seemed like they would have followed just under the other. So let's move on to example 6. I don't think they have a figure, so I'm going to do it on the same page. All right. Still clogging up. Find the derivatives of a. Y is equal to x squared plus 7x plus 2 to the negative 1/3 power. Now, just a little bit of a flashback here. This is written in exactly the form I wanted. You could have written that same problem as the 1 over the cube root of x squared plus 7x plus 2. That would have been messy. This is written in a very good form, easy, fairly easy to do. What would be your derivative of that? Let's just call it, they're going to call it d by dt, dy dt. Let's just call it that, dy dt. What would that be? Negative 1/3. Okay. You're doing the next step already. X squared plus 7x plus 2 to the negative 4/3 power. Are you through? Times the derivative of the inner function, which is 2x plus 7. All right. Now, that's a perfectly good form to leave it. There's nothing wrong with that form. Okay? However, you could write it this way. This is a numerator here. Okay, you got a minus sign, so let's put the minus sign up front. Your numerator is 2x plus 7, and your denominator is 3 times x squared plus 7x plus 2 to the 4/3 power. There's no reason to write it that way. It just is a little more, especially if you're evaluating that at some value for x, then that would be easier to evaluate, I think. But they gave it to you with a negative exponent. I would leave it as a negative exponent. So I think the first, let's see what the book. Okay. They left it in exactly that first form right there, which is fine, perfectly good. Negative 1/3 x squared plus 7x plus 2 to the negative 4/3 power times 2x plus 3. Okay? Now let's do the b part. Y is equal to e to the cosine t. Let's do dy dt. What would that be? Anybody? Say again? Okay, e to the cosine t. I was hoping you said the e first. Are you through? How did you get that? Okay, you took the derivative of the outer function, e to the cosine t is e, the derivative of that is e to the cosine t, but then what do you do for the next part? Chain rule says to take the did the first part of this of the chain rule, the derivative of the outer part, it's the same as the part was itself. But then what do we do? Derivative of the inner part, which would be what? Negative sine t. Not cosine t, but negative sine t. Okay, now again, I think I would write that, and I think the book probably does too, is negative sine t e to the cosine t. The reason for that is just so, well, number one, I like to get the sine out in front, so that pull that over. But then two, e to the cosine t, sine t, if you wrote that a little sloppily, you might think those are multiplied together, they're not. So get that out front, minus e to the sine t, e to the negative sine t, e to the cosine t. Very good. Let's see how they left it. I think they left it like that. Negative sine t, they put it in parentheses even, e to the cosine t. I don't see that parentheses are all that necessary, but if they help you see it better, use them. Okay. Any questions on, yes? Say this again now. Oh, okay. Good question. Okay, when you're taking a power function, you take the coefficient is 1. The exponent times 1, that's minus this, then reduce this by 1. So subtract a 1 from that. Well, minus 1/3 minus 1 is the same as minus 1/3 minus 3/3. Minus 1/3 minus 3/3 is minus 4/3. Right. Subtracting 1 from that power. That's how we do it. Every time you take a derivative of a power function, you subtract 1 from that power. Good question. Excellent question. Okay. Any others? Let's move on to example 7. Calculate, and they write it a rather strange way, d by dx of, well, they don't actually put the parentheses. I would tend to put a parentheses there. They don't, but it's got a grouping symbol. It's just using the, okay. The square root of 1 plus the square root of x squared plus 1. Okay. Now, I don't know about your pre-calculus text, but ours had it that once we had done composite functions, then we said you could do it as many as you wanted to. You could have an outer function that's composite, not just of two functions, but of f of g of h, for instance. That's what we've got here. You've got a square root function, outer function of this thing, but this thing has an inner function of it as well. The inner function here has another inner function of it. So it's, there's your f of g of h. Okay, so you've got three functions in there. Okay, so how do you think you would do this? What was my suggestion before? Anytime you see a radical? Yeah, write it as a power. So I would rewrite this before I try to do anything else as d by dx of, now I would use a parentheses, tell me how to write it. Anybody? Anyone have an idea? One plus, and here I see another one, so I open another parentheses. What? X squared plus 1, and that one's to the 1/2. Close that one off, and this one's to the 1/2. You see that? This square root here is that parentheses to the 1/2. Inside this is 1 plus this parentheses. Same thing in there to the 1/2. Okay? Now, how do you take that derivative? me a guess. That's just a power function, right? Same as we did before. Derivative of a power function would be the power 1/2 times 1 plus, write it all down, x squared plus 1 to the 1/2, that's to the negative 1/2, okay? Remember, whatever your inner function is, write it down just like it was, okay? But now we got to do a chain rule on the inner part, okay? You've done the outer part, so now we'll do a chain rule on the inner part. And what's the inner part of that one? Derivative of 1 is 0, so don't worry with that. How about derivative of that next part? Say again? Okay, derivative of 1 is 0. Got that. Inner derivative of that part. Let me go back to your red. Derivative of this part. We already did the 1. Derivative of 1 is 0. So now we're doing the derivative of that. And what would that be? You just did one very similar to it. Derivative of that circled in red. What would that be? It's not that hard, is it? 1/2, very good. Whoa, my pen disappeared on me. Okay, 1/2. Say again. Okay, do x squared plus 1. Write down what it is to the negative 1/2. Okay, but then you still got another inner part of it. And what's the derivative of that? Times 2x. Got it. Okay? Finally. Okay. Now, let's see if we can figure out what's going on here. Okay, first, that 2 and that 2 will go away. Okay? Now, what's left in the numerator out of all that, this thing's to the minus 1/2, that thing's to the minus 1/2, the x is the only thing left in the numerator. Okay? In your denominator, you have a 2 from that 1/2. And then this is your square root of 1 plus x squared plus 1 to the, no. Sorry, I'm writing them back. Okay. The square root of that. Okay. That's this part. The 2 is there. The x is there. Okay. The 2 is there. And then here we have, also in the denominator, a square root of x squared plus 1. All right. Those are multiplied. All right, now to me, that's a perfectly good way to write it. What they may do, and this is just a guess, is write this x, that's all that's in the numerator, 2 times the square root of x squared plus 1, and then times the square root of 1 plus the square root of x squared plus 1. I'm guessing they might do it that way just to, so you don't think this is inside here. I don't know. Let's see how they wrote their answers. sometimes it's a guessing game. All right. Oh, they left it in exponential notation, which is fine with me. The trouble is, they gave you the problem with radicals. Usually they want the answer in radicals, but not in this case. So let's go back up here and come down here. And again, what we have we have a 1/2 and x. So 1/2 x. That's this one and that one together. And then they, and I think they wrote this one next, x squared plus 1 to the 1/2 power, and then they wrote 1 plus. Yeah, they wrote it all in that. X squared plus 1 to the 1/2 power, and that's to the 1/2 power. Negative 1/2 power. And that is too, sorry. Both of those are negative. Okay. And that's how they wrote it. 1/2 x, x squared plus 1 to the minus 1/2 power, times 1 plus, open parentheses, x squared plus 1 to the 1/2 power, and that's to the negative 1/2 power. Right. It's hard to see my writing here, but if you got your book, you see it there. Okay. I'll expand that. 1/2 x, x squared plus 1 to the minus 1/2 power, times 1 plus x squared plus 1 to the 1/2 power, and that's to the minus 1/2 power. Okay. That's how they wrote their answer, which is a strange way of writing since the problem originally had radicals. They changed it back. Okay. I told you before that usually if you see trig functions, assume they're in what mode? Radian. If you happen to run into a problem where you are in degree mode, and I'm not familiar with this notation at all. If they underline the trig function, that means you're in degrees, okay? So sine underline x would be sine of x degrees. And I don't think I've seen that anywhere except this text. I'm not saying that's standard by any means. It may be. I've just never seen it before, okay? So, going to clear this out here completely. Okay. And when they write sine underline x, they means the sine of x degrees as opposed to sine of x radians. Okay. So what that means, and y'all should remember this from trig, do you? How do you go from degrees to radians or radians to degrees? So let's say you had x degrees, okay, and you want to multiply that by some value to get you radians, okay? Say again? Okay, 180 is involved with it. Here's what I do. Anytime I'm making a conversion, no matter what kind of conversion it is, I use these train track type things. Here is your number, it's a variable in this case, there's your unit. This line represents numbers, that line represents units, that line represents number, and you're going for a unit, okay? I suggest always put the units in their place. You're going from degrees to radians, so always decide what goes where here. One goes on top, one goes on bottom. What would go on top, what would go on bottom? Units. You're trying to get from degrees to radians, so put your units in their place first. What unit goes on top, what on bottom? One's degree, one's radian. Which goes where? Degrees on top, is that what you said? Okay, if you put degrees on top and multiply it and put radians on the bottom, when you multiply that, you get degrees squared per radian. I don't know what that is. Okay, so I don't want to do it that way. Okay, so guess what other way we would do it? Only one other option, isn't there? Radians on top, degrees on the bottom, and guess what? Degrees will cancel out, and that leaves your radians right where you want them, right? Now, the question is, how many radians are equivalent to how many degrees? Okay? And you're saying 180. 180 would refer to which? Radians or degrees? Okay. All right. Let's go back to a circle. Okay? How many either degrees or radians is it all the way around that circle? Second? 360 what? Degrees. So 360 degrees would be how many radians? Second? 2 pi, you're exactly right. Okay? Now, because both of those are divisible by 2, I would write that as 1 over 180. And if a full circle is 360 degrees, what's half a circle? 180 degrees, and how many radians is that? Pi, exactly. Okay? So pi radians is always 180 degrees. And vice versa, 180 degrees is always pi radians. So that's where they get the thing. This would then be the sine of pi over 180 radians. X is in degrees, and there would be an x here too because you multiply through by x. Pi x, yeah. So it'd be, that's where that comes from. Okay? Now, I don't know why they even mess with this, but they do. Okay? So let's do d by dx of sine x, where x is in degrees. What would that be? Well, your outer function is sine. What's the derivative of sine? Derivative of sine? Cosine of pi over 180x. And then the derivative of the inner part is derivative of the inner part, pi over 180. And that's why he said at the very beginning by a weird factor of pi over 180. And that's exactly what you get here. Anytime you're dealing with degrees rather than trig function, degrees rather than radian, you've got to take care of that as well. Okay? It says a similar calculation shows that the factor pi over 180 appears in formulas such as derivatives of other standard trigonometric functions with respect to degrees. Derivative with respect to x of tangent in degrees x be pi over 180 times secant squared. Not pi squared over 180 squared. It's just pi over 180 times secant squared. Okay? And that's exactly what you get here. And this would then be the equivalent to pi over 180 cosine underline x, because this thing here is, that's your conversion to go back and forth. Okay. Now, they do a proof of the chain rule here. They waited till the very end to do it. And it's not a super simple, but it's not that bad of a proof. It just takes a lot of space. Okay? The old book had a shifting and scaling rule that either this book doesn't do at all, this edition doesn't do at all, but I really don't see any reason for it because it's all taken care of in the chain rule. So we'll just talk through it right now, and then I'll probably write it down in just a minute. Well, it's written right here. If you had d by dx of a function of something that has been scaled upward, this is multiplied by a constant and something added to it, okay? Well, you have d by dx of f, so L prime, times the derivative of the inside is just k. So that would be k L prime kx plus b. And frankly, for me, I see no reason to do a special theorem for it. I'm with the new edition. It's just straightforward application of the chain rule. That's all. So I don't see any particular reason to do it. Okay. Unfortunately, I hear people summing up. That was the end of the section, I think. This just shows a scaling thing there. And here's part of your proof of the chain rule. This is your equation 1 they have there on page 163. That's it. I take it, do y'all think preliminary questions would be useful in this section? Yay or nay? No? Okay. Homework exercises here then. Either 1 or 3 or both. Do number 5. Okay. Then any of the odds, either 7 or 9 or both. Then any of the odds 11 through 21, either 23 or 25 or both. Do 27. Any of the odds 29 to 41. Any of the odds 43 to 71. There's a whole passel of them there. And then either 73 or 75 or both. And then the couple of application problems. Do any of the odds 77 through, I guess it's 81? No, 85. No, yeah. 77 through 79. Either 77 or 79 or both. I'm sorry. Any of the odds 77 to 81. Then do 80. I swear. They've got this in here backwards, it looks like. Let me back off. Any of the odds 77 through 85, okay? And then either 87 or 89 or both, and then any of the odds 91 to 97. Now, back up just a minute. There is a Bertalanffy's, I guess is how you call that growth function, actually von Bertalanffy's. He was a biologist, so don't worry about maybe writing on him, but how is that used in biology? If you're a biology or bioengineering major, you might run into that, so that may be of interest to you. And then on 94, even though you don't have to do it, there's this Stefan-Boltzmann law, which is used tons in physics. So I'll let you decide whether you want to, what you want to do with that. Who was Stefan, who was Boltzmann, and how is this law used? And that's all. So we'll start next time in 3.8. Any questions? Got quite a bit covered today. And by the way, 3.8, go back to the beginning. We'll do 3.8 implicit differentiation. Then we'll do derivatives of general exponential and logarithmic functions. And I'd love to do related rates. I just don't think we're going to have time, especially since we've now lost a week and a half of the summer. If you think Monday was Memorial Day, then we had a weather day on a Wednesday, didn't we? And now we've had a unexpected holiday on the 3rd of July, so we've lost 3 classes out of 20. Okay, so we're down to a 8.5 week term rather than a 10-week term. So I think we'll have to skip 3.10. Good deal. Thank you. All right, and we'll pick up and go. So I'll try to have your test ready for you next time. I don't know if we'll be ready for it, but I'll try to have it ready. Thank you. Good deal. And for those who came in late, I did get all your grading done over the weekend, but I haven't gotten it all on Blackboard. I'll try to get that done tomorrow if possible. Good deal. Will someone say something to me? Sure.
Is it okay just like grade first? I want to know.
Yeah, you did quite well on both. See, your paper you got a 99, and your test you got a 95. Good deal. Huh?
No, gotcha.
I'm sorry?
No, I'm not gotcha.
Okay. Okay. Yeah. And when we've got time, if you get here early one day or something like that, I'll let you see your paper. I mean, you see your test. I can't return them until I get them all in, but I'll let you see them. Okay. Okay, surely.
Did you get my email?
I recorded that. Sorry, huh?
Did you get my email?
I saw it, but I haven't had a chance to read it. Yeah, sorry.
And I completed my test. I'll turn it in Monday
Okay. Okay. And don't forget about your paper either.
All right.
Okay, good deal.